The topic of this video is section 4.4 Conics part 2. In part 1 we covered ellipses and parabolas and their standard forms, and so now we're going to be talking about just a little bit about circles. There's not a lot to say there, but we will talk mostly about hyperbolas. So in hyperbolas, the definition of a hyperbola, well, it's similar to that of an ellipse, and the difference is that for an ellipse, the sum of the distances between the foci and some point on the ellipse is a constant. Now, whereas on a hyperbola, the difference of the distances between the foci and a point on the hyperbola is constant. So we'll get into that and show you on these figures here. Definition of a hyperbola. A hyperbola is the set of all points x, y in a plane, the difference of whose distances from two distinct fixed points, foci, is a positive constant. So let's take a look at this picture right here and really see what that means. I'm going to go ahead and take a red pen here and show you that this distance right here marked D1 and this distance here marked D2. Notice each of those distances from a single point, xy, on the hyperbola, is that distance is measured to each focal point of the hyperbola. So notice here's a focal point on the upper part right up here and another focal point here down below. Now, if I measure those two distances and call one D1 and the other one D2, and I take the longer and subtract the shorter, I will always have the same value on any point on the hyperbola. So if I wanted to do it again, I could take a point maybe up here on the upper branch of that hyperbola and measure this distance and call it D3, and measure this distance right here and call that D4. And if D3 is longer than D4, so if I took D3 and subtracted D4, I will get that same constant. I'll just call it K, but it's going to be the same constant that's being talked about right there. So that's what the definition of a hyperbola is. And notice there's some similarities and there's some differences about how it relates to an ellipse, and that's what that is. Now, the graph of a hyperbola has two disconnected parts called branches, because one comes from the upper nap of the cones and the other one comes from the other nap of the cones. So those two branches then are the line drawn by the hyperbola. The line through the two foci that intersects the hyperbola at 2 points called vertices, so that would be a vertex right here and a vertex right there, two of them, so we call them vertices. The line segment connecting the vertices is the transverse axis. So that's this guy right here, this length that goes straight through both foci and the vertices and the center of the hyperbola. That line is called the transverse axis. And the midpoint of the transverse axis is the center of the hyperbola. Okay, so as we get into talking about this, we're talking about the standard equation of a hyperbola with its center at the origin. In the discussion of the standard equation of a hyperbola, where the center is at the origin, we're talking about A not being equal to 0 and B not being equal to 0, where you see x squared over a squared minus y squared over b squared. And that's when the transverse axis is horizontal. Another version of the equation is y squared over a squared minus x squared over b squared is equal to 1, and that happens when the transverse axis is vertical. The way you want to think about this is that remember in an ellipse you cared about whether A or B was larger, one was larger than the other. Here we don't. B could be larger than A and we still have a hyperbola. The important thing is how the hyperbola is positioned as far as the transverse axis being horizontal and vertical. So X is always paying attention to a horizontal line because it goes from left to right. Notice the position for a squared on when the transverse axis is horizontal. We've got x squared over a squared. When the transverse axis is vertical, we know that y pays attention to a vertical line, and so now we have y squared over a squared gives us the transverse axis as being vertical. The vertices and the foci are, respectively, A and C units from the center. So A is this distance that the vertex is from the center, and C is the distance the foci is from the center. Let's take a look at the picture of what that means here. If we look at the picture, you see the points A, 0 and the point C, 0. C is the location of the foci, and I'll go ahead and mark those in red right here. There's one at negative C0, and there's one at C, 0, and here are the vertices of the hyperbola at negative A0 and A0. And we'll talk about this later in a little bit, but there's the distance B on that line that is perpendicular to the transverse axis. Similarly, if we have a vertical transverse axis, then our hyperbola looks like this. Notice C is the distance from the center and down to up to 0, C and down to 0, negative C. Those are the focal points. The vertices are on the transverse axis at the hyperbola, and we have the center here right at the origin. And then there's our distances B again on a perpendicular that passes through the center. Okay? The relationship that A, B, and C have, as far as just calculating them are concerned, is very Pythagorean. It's A squared plus B squared equals C squared. So all you have to do is think of Pythagorean theorem, and that's going to give you the relationship that the distances of A, B, and C are with each other. So let's take a look at example 1 and find the standard equation of a hyperbola. So here is a hyperbola that's given to us in a figure, and it has foci located at negative 3, 0 and at 3, 0, and vertices located at negative 2, 0 and at 2, 0. So this is going to tell us then that little a is equal to 2 because the vertices are 2 away, and that little c is going to equal 3. So if we want to figure out what b is going to be, that's going to be pretty simple because we know a squared plus b squared equals c squared. So let's just go ahead and fill those pieces in. We've got 2 squared plus b squared, which we don't know, is going to equal 3 squared. And so that's going to be 4 plus b squared is equal to 9. Subtract 4 and get 5. And that's what b squared is. So when I take the square root of both sides, b is going to equal square root of 5. So if b is equal to square root of 5, now we can go ahead and write the equation. We're going to be looking at the equation that starts off with x squared over a squared minus y squared over b squared, and that's equal to 1. And the reason why is because we're saying that x squared is over a when the transverse axis is horizontal. You see that the transverse axis is indeed horizontal here, and so that's why we have that. So now all we have to do is plug in the numbers. X squared over 2 squared minus y squared over root 5 squared is equal to 1, and that is the equation for our hyperbola in this example. So You're going to find that we're going to be caring a lot about these things called asymptotes of the hyperbola. An important aid in sketching the graph of a hyperbola is the determination of the hyperbola's asymptotes, as shown in the figure. Each hyperbola has two asymptotes that intersect at the center of the hyperbola. Furthermore, the asymptotes pass through the corners of a rectangle, or we call this the box, with the dimensions of 2a by 2b. The line segment of the length 2b joining 0b and 0 negative b, or negative b comma 0 and b comma 0, is what's referred to as the conjugate axis of the hyperbola. So we've talked about the transverse axis, which contains the foci and the vertices, and that perpendicular line that passes through the center is referred to as the conjugate axis. So just know where your transverse axis is and your conjugate axis is, and that gives you a good guide for how to write the equation of a hyperbola. So look at what happens here. If you create a box, I'll go ahead and outline it in red. If you create this box here, then it's actually not that difficult to find the points that are the corners of the box by the fact that you know the length of A and you know the length of B. And it's just that distance from the center of the hyperbola that gives you those corners. If you write the equations of those lines, you end up creating what are called the asymptotes of the hyperbola. And you'll notice that the hyperbola, as it is being drawn, actually heads in the direction of and gets closer and closer to the asymptotes, and that's why they're called the asymptotes. And so that's how the hyperbola is created. So there that is for the horizontal transverse axis. Here's the picture for the vertical transverse axis, and notice in both cases we have a box, and we can actually write the equation of the lines that are the asymptotes. So here we go, the equations of the asymptotes of a hyperbola with the center at the origin. Notice with the center at the origin, the y-intercept is always going to be 0, right? Because these things cross right at the origin, and so we're just going to have y is equal to mx without the b. So m is going to be, when the transverse axis is horizontal, it's going to have a slope of b over a and negative b over a, and that's going to be the slopes for the line that is the asymptote of the hyperbola. When the transverse axis is vertical, then the slope is going to be a over b, not b over a. And so we have a over b and also negative a over b, creating the asymptotes of our hyperbolas. So here's the picture, and you can see that the asymptotes have the equations y is equal to b over a x, and the for the horizontal transverse axis, and the asymptote of negative b over a x, and for the other asymptote of the horizontal transverse axis. When the transverse axis is vertical, there you can see that the asymptotes are y is equal to a over b x, and y is equal to negative a over b x. And so there's the asymptotes of a hyperbola. So if I wanted to sketch a hyperbola, this is where this becomes really handy. So they gave you an equation, and that equation says 4x squared minus y squared is equal to 16. Let me just show you how we convert that given equation into the standard equation for a hyperbola. So standard equation of a hyperbola is going to equal 1. In this case right here, we have equal 16. So I'm going to divide both sides by 16. everything by 16. So that looks like that now. 4 into 16 gives me a 4 down in the denominators. That's just going to be x squared over 4 minus y squared over 16. Now conveniently we have squared terms in the denominators, and so we can write them as squared terms. X squared over 2 squared minus y squared over 4 squared. So here you can see right away that we have a horizontal transverse axis. And because we have x squared over a squared, so we know that this guy right here is going to be our transverse axis. It's going to be horizontal there. So I'm going to say that a then is equal to 2 and b is equal to 4. So here's how we draw the box now. We're going to go from the center, which is at the origin right now, and we're going to go find the vertices. Well, that's going to be 2 to the left at negative 2, 0, and 2 to the right at positive 2, 0. And there are the vertices for my hyperbola. B is equal to 4, so I'm going to go up the y-axis, 1, 2, 3, 4, and put a point right there. And that's the distance b up, and I got to go the distance b down. 1, 2, 3, 4. And I'm just going to go ahead and draw a box now. And I'm just using dashed lines in order to draw it. And you'll notice, let's just do it from the origin here. I'm going up 4 and over to the right 2. So my slope then is up 4 over 2 is just 2, a slope of 2. If I go down, I notice that my slope over here is going to be negative 2. So I know then that my asymptotes are going to be y is equal to 2x, and over here y is equal to negative 2x. So now all we have to do is go from our vertices and head toward the asymptotes in order to draw the picture that shows my hyperbola. And you just head toward the asymptotes, and that's a pretty good approximation of the appearance for your hyperbola. So there we go. So that's that example, sketching a hyperbola. Now let's find the foci. Well, we have a squared plus b squared is equal to c squared, and that's going to be 2 squared plus 4 squared is equal to c squared. So that's going to be 4 plus 16 is 20. So I get 20 is equal to c squared. Take the square root of both sides. And that's going to be 2 root 5 is equal to c. So 2 root 5. Well, root 5 is 2 and a little bit more, and times 2, so it's going to be 4 and a little bit more. So that makes my foci going to be all the way to the left, 4 and a little bit more. And there's my focal point there, and to the right 4 and a little bit more, and there's my focal point. So I can say focal point and focal point, and there's a good picture of that hyperbola. So in example 3, we're going to find the standard equation of a hyperbola here. Find the standard form of the equation of the hyperbola that has vertices of 0, negative 3, and at 0, 3. So I know that little a, do that in yellow, little a is going to equal 3. And my asymptotes are going to be y equals negative 2x and 2x as shown in the figure there. And so doesn't that mean then that as we're drawing the box for the asymptote, the upward part is going to be 3, so that means that 2 means that b is going to be 1.5. So I think I can just go ahead and say that b is going to equal 3 over 2, I'll say. And that should take care of that. So there's that. We're trying to write the standard form of the equation, and we have everything that we need. So we can say that this is going to be y squared over a squared, right? So it's going to be y squared over 3 squared minus x squared over, and we'll just write it this way, 3 halves squared. Okay, let's fix this up a little bit. This is y squared over 9 minus x squared over 9/4. And this is equal to 1. And that's pretty much it right there. Now we can clean this up a little bit. So when we do this right, it's going to be y squared over 9 minus, and we're going to call that 4x squared over 9, and that equals 1. And there is the equation of our hyperbola. Now we wanted to spend a little bit of time reminding you of the equation of a circle. So if you remember, the locus definition of a circle simply is stated this way, that the set of all points, x, y, that are equidistant from a single point called the center. So we're going to call the center hk, and this is based on the distance formula. So if you remember, the distance formula says the distance between those 2 points, x, y, and hk, are simply the difference of the x's squared and the difference of the y squared added together and then taking the square root. Very Pythagorean. So distance then is equal to the square root of x minus h squared plus y minus k squared. Now, the distance is the radius of the circle, and so when we do that and we square both sides of the distance formula, we end up with this equation right here of r squared is equal to x minus h squared plus y minus k squared. Now, finally, if we're talking about the center being the origin, then h and k are 0, 0. So x minus h is just simply going to be x squared. And so now we're down to, if the center of the equation of the circle is at the origin, then we're looking at r squared is equal to x squared plus y squared. So here we have it. There's a circle that is 3 units from the center. And so that's just simply going to be 3 squared is equal to x squared plus y squared. And that is the equation of our circle right there. Okay? So here we are, and the homework is 2-part. One's on page 367. I want you to do problems 7, 9, and 10, and then do all the parts of 61 through 77, just the odds. And I want you to do 4 more problems, if you could, please. Go to page 382 and do problems 65 through 68 all. That will give you 16 problems. Go ahead and do those. If you need to, give me a call or let me know that you want to meet, and we can go over this homework together.